Hi, and welcome then to this recording where we are going to be looking at linear programming. Okay, so we are continuing on with topic 7. We've already looked at limiting factor analysis, and you should have already looked at your linear programming introduction. During the introduction, we stated that we use linear programming where we have more than one constraint, and what we are going to use is DOF-PIs. And DOF-PIs are essentially a set of instructions. So we've got 6 steps, and they will take us through the whole linear programming process in terms of identifying exactly what the optimal product mix should be, and also what the maximum contribution or profit is that we can earn under that basis. So this recording then is basically taking you through the calculation. So if ever you get stuck on the whole concept of linear programming and lose your way a little bit in terms of how the whole thing looks, then please come back to this recording. As I explained in the previous recording, from an exam standard perspective, the questions that we're going through for tutorial purposes here aren't going to be the same as you're going to get in your objective test. Okay, and that's because this would effectively be worth around, let's say, 14 to 15 marks. And obviously your questions are just 2 marks, but sometimes they can amalgamate the data, so they give you maybe 3 answers to give on one data set, which would then equate to 6 marks. But even so, you're not going to get a full linear programming question. However, you will be asked to dip in and out of linear programming along the ways of DOF-PIs. Okay, so you're going to have to be able to understand what has already been done and what needs doing further. Okay, so what we're going to do is we're going to use apply your knowledge to in your notes, and this is going to demonstrate for us exactly how we put DOF-PIs into place. In terms of the requirement, you are being asked to state the objective function and the constraints. So effectively, you're going to have to do DOF, okay, define the variable, state the objective function, and formulate the constraints. You are then asked to draw a graph to illustrate the constraints and the feasible region, and then solve for the optimal solution. So they're asking you to do your points to plot and your ISO contribution line, and then we can finish off by proving that all of this is correct by undertaking a simultaneous equation. So we can undertake our pies. Let's have a look at the scenario first of all then. We've got a company who are producing 2 products in 3 departments, and they want to maximise the profit. The production details and contribution are shown below. So we've got product X and product Y. Department A means that product X must spend 8 hours in there and product Y must spend 10 hours in there. We then have department B, and product X needs 4 hours of department B's time, and product Y needs 10 hours of product B's. Product X needs 4 hours of department B's time, and product Y needs 10 hours of department B's time. And then finally, we've got department C, and product X needs 12 hours of its time, and product Y needs 6 hours. We are then being told that we have got a contribution value of 4 for X and 8 for Y. We are also then told how many of our hours are available in each of our departments. So these are your constraints, okay? This is stopping you from being able to make as many as you can because there are only a certain number of hours available in each department. So we need to understand that given the constraints that we've got in terms of these hours, how many of X and Y should we produce to maximise our profit? Now, we haven't got any profit figures, but we have got contribution figures. So we're going to use this to state our objective function, and that is going to be O of DOF, okay? So we've got our constraints. So let's have a look then at how you should pull this together. Now, I'm going to show it obviously in long form. You need to be able to prepare these calculations depending on the elements that you're being asked, okay? But we'll keep it all written out neatly so that you can follow back on these numbers from a tutorial perspective. So we're undertaking Apply Your Knowledge To, which is linear programming. And we're going to start off then by just stating our steps. We've got DOF pies. So first of all then, we need to define the variables. Now in this particular instance, our products are already called X and Y, which is fantastic. If that wasn't the case, and if we had, let's say, the xylophone and the yo-yo, okay, we don't want to be writing that out every time. We just need to make things simple for ourselves. Even if they were called the widget and the smidget, or the bip and the bop, whatever they would be called, every single linear programming question that you undertake, you will make sure that one of your products is then related to as the product X, and the other is going to be known as product Y, whatever they're called. Okay, and this makes it easier for you to handle every single time. So by defining the variables, we say let X equal the number of product X that we're going to make, and let Y represent the number of product Y that we are going to make. Okay, so if they were called xylophone, you'd say xylophone here and yo-yo here. Okay, all we're doing is putting these into shorthand. Okay, so that's D done. Next is O, and O is to state your objective function. So this is about saying, well, what is it that we're trying to achieve? Now, the scenario tells you you're trying to achieve maximum profit. Okay, therefore, you need to calculate the profit per unit, or it will say maximum contribution, so you need to identify contribution per unit. In this particular scenario, we've got a contribution per unit. To get to a profit figure, you take off your fixed cost, but we haven't been told any. Therefore, we'll use the contribution figures as our objective function. So in other words, we get 4 for every y and 4 for every x, 8 for every y. So we're going to make $4 contribution every time we make an x, and $8 contribution every time we make a y. And that is your contribution per your objective function. And what will happen is when you get to the end and you need to answer the question and state what the profit or contribution is that you can earn, you simply multiply 4 by the number of product X and multiply 8 by the number of product Y. And what we have to do, the rest of DOF pies is going to help us figure out what these numbers actually are. So that's our objective function, which is very straightforward. You now need to formulate your constraints. Okay, so formulating the constraints is just about taking the information that you've got in the scenario and turning it into a sum, okay? And you have to do it for each and every constraint that you've got. So we're going to start then with Department A. Department A needs 8 in every X and 10 in every Y and has a maximum of 11,000 available. So we say Department A needs 8 for every X, 10 for every Y, and that value must be equal to or less than 11,000 hours. You then need to go on to your next constraint, which is Department B. For Department B, we need 4 in every X and 10 in every Y. And we've got a maximum of 9,000. So Department B shows that we've got 4x and 10y, but that must be equal to or less than 9,000 hours. Finally then, we've got one more constraint. We've got Department C, and Department C needs 12 for every x, 6 for every y, and a maximum of 12,000. So we've got 12 of x, 6 of y, equal to or less than 12,000 hours. So in terms of constraints, you're going to have a minimum of 2, because remember we do linear programming where there are more than one constraint. However, I can't imagine there being more than 3, because you can see this is very repetitive. And so once you've identified how to formulate one constraint, you could do it for 50 if necessary. Okay, so you're proving your point that you can do it. The only other thing we need to be mindful of is, at this point here, we need to state that there is also a non-negativity constraint. And that is your other constraint. And that means that both x and y must be greater than or equal to 0. So this means that you must make at least 0, which means you can't make a negative product. So what we can't do is make, let's say, a negative 500 Ys to create another 5,000 hours for Department A. You can't make a negative product to increase your resource. It's impossible, isn't it? Okay, if we're making chocolate bars, we can't make minus 300 chocolate bars to create more resource. It's just not going to work. So you must make at least 0. You cannot make a negative amount. Okay, and so they could ask you about non-negativity. They could ask you what it means. They could ask you, you know, what this means in terms of being a constraint. They could list down the constraints, and you have to pick out all of the constraints, and you need to know that non-negativity is one of them. The other thing that you might also be given, as opposed to non-negativity, is you could be issued with minimum or maximum demands. And if you were, again, you need to state those constraints. So for example, if it said, do you know what, we can only make 500x, then what we'd have to say is x has got to be equal to or less than 500. And if we can only make 300y, then we would put that down. You might also have a contract that says, but we've got to make a minimum of 50 of each. Okay, therefore you'd have to make at least those. So it's stating down what your constraints are. And these will help you because these form part of your answer. And if you don't put these on, then as you go through the question, you won't be getting the right answer. Okay, and again, in your objective test, they could ask you to drop a line onto a graph, and you need to be able to understand that your minimum and maximum demands also form part of your graph. Okay, but in this particular question, we don't have any minimum or maximum demand. So I'm just going to say here that this is example only, not required in this particular question, and apply your knowledge to. Okay, I want you to remember that it's there, but I don't want you to get confused and wonder when we do the graph why I'm not plotting it. And it's because it's not relevant to this particular question. Okay, so that's your non-negativity and your minimum and maximum demand dealt with. Your non-negativity is relevant to this one because there isn't a minimum demand, therefore we state non-negativity. So what have we done then, guys? We've defined the variables, we've stated our objective function, and we've formulated our constraints. So we've completed DOF, and that completes part A, which is to state the objective function and to formulate the constraints. The next step then is to move on to your pies, which is obviously always the best bit. And we need to draw a graph and basically finish off with pies. So what we're going to do, put another page in. So I'm just going to remind you of our steps, DOF pies. We've completed define the variables, state the objective function and formulate the constraints. We're now on P, and P are your points to plot. Now your points to plot is all about taking the constraints and from the constraints identifying coordinates that then make up your lines on your graph. Okay, so points to plot is all about identifying what points you need to plot on your graph. So you need to take each constraint in turn as you've formulated them. So first of all, we need to take department A, 8x plus 10y is equal to or less than 11,000 hours. So you simply write that back down. Now what we're going to do in order to get our coordinates, we're going to say that when x is 0, when x equals 0, 10y must equal 11,000. Okay, because we're not making any of x, therefore we're going to make them all into y's. So how many y's could we produce then for 11,000 hours if each takes 10 hours? We could produce 1,100 y's in department A. And what that's done is given you a coordinate for your y-axis of 1100. So these are your x coordinates and these are your y coordinates. Now what you need to do is flip that around to get your x coordinate and say, well, okay then, what happens if y equals 0? Well, what we have is 8x, which must equal our 11,000. Therefore, x must equal 1,375 units. So if we didn't make any of y, we could still make 1,375x. That gives you your x coordinate, which is 1,375. So now what you've got for department A are two coordinates, one on your y-axis, one on your x-axis, and when you join them together, you will make a line. Okay, but we'll do all of the lines at the same time. And in your objective test, you might have to find out what these coordinates are. So you need to be able to complete this calculation so that you can identify where your coordinates would be. You're obviously not going to have to compile a full graph, okay, but you need to be able to know how to do it to be able to explain the elements they ask you. Next then is department B, where we have 4x and 10y. So we take the next constraint, department B, 4x plus 10y must be equal to or less than 9,000 hours. So we say when x equals 0, 10y must equal 9,000. Therefore, we could make 900 y's. Okay, if we didn't make any x's, we could make 900 y's. However, when y equals 0, for x then equals 2,200, oh no, sorry. For x equals 9,000, therefore x must equal 2,250. So you now again have coordinates. Your y coordinate is 900 and your x coordinate is 2,250. Okay? So repeating that again then for Department C, and what I'd like you to do is have a quick go at doing it based on what we've already done. So just pause the recording and have a little go. Okay, so hopefully you've come up with an answer. The answer should be as follows. 12x plus 6y is less than or equal to 12,000 hours. So we then say, when x equals 0, 6y equals 12,000, therefore y equals 2,000. However, if we flip that round, when y equals 0, then 12x must equal 12,000, therefore x is 1,000. So we have 2,000 as our y coordinate and 1,000 as our x coordinate. And what you've now completed are all of your constraints, all of your points to plot. You can now draw the graph. And as I say, you're not going to have to do that in the exam, but you need to understand how it's put together. So what we're going to do is first of all understand how big our axis needs to be. So we look at the largest value of our x coordinates, which is 2,250, and then the largest value of our y coordinate, which is 2,000, and that gives us our graph size. Okay, now what I suggest you do is if you go onto Google, you can just type in graph paper and then print yourself some off. You don't need to go out and buy any. Doesn't matter if you haven't got any at the moment, just do the best you can. I promise you, when using a ruler and graph paper, it does all work out absolutely accurately. Okay, so you've got your y-axis on the left because a y goes down, and then you've got your x-axis running across the bottom. So now you need to populate your graph. So we're going up to 2,000 on our y-axis. So we'll go up in twos, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 200, 400, 600, 800, 1,000, 1,200, 1,400, 1,600, 1,800, 2,000. And then going across our x-axis, we're going to go up to 2,300. Okay, so I'm going to go up in 100s here because I've got more room. Okay, so now we've got our graph mapped out, what we can now do is take the coordinates and pull our graph together. And this is something that you could be asked to do. So you could be given a number of lines, and what you have to do is drag and drop them in the right place. Or you could be given a little X symbol, and again, you have to move that and drop it in the appropriate places. Okay? So you're not going to have to draw it with a calculator, but you certainly may be asked to populate it. So first of all, then taking department A, we've got a coordinate of 1100 for Y. So we'll plot that on Y, 1100, and 1375 for X. So 1375, which is going to be about here. And now you just need to join the dots. So I can't use a ruler on here because it just doesn't allow me to do it. So I'm going to try and get it as straight as possible. It's way off. Okay. And that is Department A's line. And again, you need to label them. And that might be what you're asked to do in your objective test. They might put all these lines on a graph, and all you have to do is label them up. And so by understanding your coordinates, you can label appropriately. Department B then, we've got 900 for Y, and we've got 2250 for X. So all the way down here. If I get this straight, then I'm the tooth fairy. That's not too bad, is it? She says. Okay, so this is going to be Department B. And then finally, Department C, we've got 2000 and 1000. So 2000 here, 1000. So taking that down to there. Okay, so that's your coordinates. If you had a minimum amount of, let's say, 50y, you would obviously then put a line going across for your minimum. And if you had a maximum, you'd obviously also put your maximum line on and label them accordingly. But we haven't got any of those in this particular instance. We have got the non-negativity, which means we have to make at least nothing. We can't make a negative. Just label up Department C. So what you now need to do is a little bit of colouring in, okay? And the colouring in is basically to go within all of the points that could be a potential for actually production. So we need to colour inside all of the intersects. So we'll start at 0 here. And at the point you come to a line, you need to stop and make a turn. And keep going down. Then you come to another point, so turn down. Another point, turn down. Another point, turn down. Okay, until you've coloured all the way round. Now what you need to do is just follow those round and label these points up. So all of the points of intersect are potential production levels. So obviously we could make 0 and 0, we could make 0 and 900, we could make whatever that is, and then finally 1000 and 0. So what you've now done is you've labelled all of your intersects, A, B, C, D and E, okay, in the coloured in region. And this then, guys, is known as your feasible region. And again, this could be something that you have to label up and therefore worth 2 marks to you. So you need to know that that is your feasible region. So what we're saying is, given all of the constraints that we've got, actually within this area here is where our answer lies, okay? We can't go outside of this because if we do, well, quite simply, we won't have enough of one or all of our resources. So if we decided to produce up here, which is 12,000 and 2,000, we won't have enough resource in either Department B or Department A, because actually their limits are within their lines down here. Okay, so your feasible region has been highlighted. Now what you need to do is find the answer out. And in order to find the answer, there are a number of options. You could take each of your intersects, apply the contribution, which is your objective function, and see which one makes the most contribution. That's called the walk round approach, and it takes you a long time to do. So we're not going to do that. The approach we're going to use, and what you'll be expected to use in your exam, is basically the next step on your DOF pies. Okay, so I'm going to put another page in there. So going back to DOF pies, we completed our points to plot and we drew our graph. The next thing is I, and I is your ISO contribution line. Now your ISO contribution line is basically another line that we're going to put on our graph, and it will show us what the answer is. Okay, so what you need to do is you need to take your objective function that you identified back in O of DOF pies. So you need to take this objective function down to your ISO contribution. So we said that 4x plus 8y is going to give us maximum contribution. What you then need to do is make up a contribution figure. Now, what you want that figure to be is entirely up to you. However, what I can say is that you need it to ensure that you can put a line on your graph that is within, excuse me, that is within your graph parameters. So we need to place another line on this graph, and we're looking for a line either around here or around here. Okay, if it's going to go outside the graph, we're not interested, and if it's going to be so small that it's down here, again, that's not any good to us, and you'll see why in a moment. So you assume a contribution. You can start with anything. I'm going to use 3,200. Once you've done that, you then calculate the coordinates exactly as we did before, nothing different. So we say, let's keep it in the same colour. We say that when x equals 0, 8y must equal 3,200. Therefore, y equals 400. And if we flip it round and say, well, when y equals 0, we've got 4x equaling 3,200. We then know that x must equal 800. You then go back to your graph and plot those lines. So we've got 400y and we've got 800x. So you then join the dots again and label it up ISO contribution line. And again, this could be something that you just have to label in your exam, or they may ask you to plot an ISO contribution line or explain what one is. Okay, so now we've done that, what you need to do is you need to take a ruler or a piece of paper on that ISO contribution line. I'm just going to show you on the camera. Okay, so just bear with me a second. Okay, just trying to get that in there. Okay, so you can see this is my hand-drawn graph, and you can see I've got nice straight lines. You can see my feasible region, and you can see my ISO contribution line. What you need to do then is take a ruler or a piece of paper and you put it on your ISO contribution line. And the idea is that you are obtaining an angle. Okay, so that's the angle. You then push up through each of the intersects that you've labelled in your feasible region, whilst maintaining this angle that your ISO contribution line has given to you. So we push up and out, and you'll see we pass through E, we pass through D, and we pass through B, and the last one then that we're going to pass through is right up here, and that's C. Okay, so just take your ruler or your piece of paper and push through those intersects. Okay, the last one that you get to is your answer. Okay, that's how it works. So the last one we get to is C. That's our answer. Now, if your ISO contribution line was above your feasible region, you push down at the angle of the line, and this time it would be the first intersect that you come to. That would be your optimal solution. That would be your answer. Okay. Now, what happens if you end up with a line that is really small for your ISO contribution line, so it's down here, excuse me, you won't have enough of a line to make an angle, and therefore when you're trying to then push it through your intersects, you could go through any because your angle's not it's not strong enough as an angle. Okay, equally you don't want it outside of the graph because then you've got to draw a new graph, and we don't want to do that. So that's why we wanted a line that's kind of about halfway in your ISO in your feasible region or just outside of it. Now, what if you'd have said, well, my contribution that I assumed was about 10,000 and therefore the line was too big? All you do is you either take a naught off your contribution that you've assumed. So you'd take a naught off, or you'd add a naught on, or you'd half it, or you'd double it. Okay, and that way you will end up with a line that is about sensible. Okay, so just sorting my paperwork back out. All right, so I'll turn my video off. So now then, you've got your ISO contribution line. We've had a look to see which intersect it passed through, and it passed through C last. Therefore, again, you need to label that C is your optimal solution. Okay, now if you were to do a walk round of that and do the calculations at each intersect, it would have taken you longer than coming up with an ISO contribution line and seeing which you pass through first if we're going up, last if we're going up, or first if we're going down. Okay then guys, stay with it. We've just got one left to do. We've now seen that the answer is going to be that Y is going to be around here and X is going to be around here. Now bear in mind, I haven't used rulers and stuff, so my graph is out, okay? And again, depending on what you've done, it would be out too. But as you can see from the one that I showed you that I'd hand drawn on my graph paper, if you'd look there at the optimal solution, it is in just a slightly different place and more accurate. Okay, but unfortunately I can't do that on the screen. So what we're going to do now is we're going to prove that C is indeed the correct answer. And so we need to complete our last stage of DOF pies, which is the S. And the S is going to be your simultaneous equation. Now, some of you may have done these a lot before, some of you may not, which is absolutely fine. Okay, what you need to do is you need to take the two constraints that created the intersect of your optimal solution. Okay, so remember on this question we had three constraints. The intersect of your optimal solution can only be caused by two of those constraints. And in this particular case, the two constraints that create that intersect and therefore our optimal solution are department A and department B. So what we're going to do is we are going to take the constraints for department A and department B that we formulated back up here in F of DOF pies. So we simply take down our our constraints. So we've got 8x plus 10y was equal to or less than 11,000 hours. And then we take 4x add 10y equal to or less than 9,000 hours. What you then need to do is deduct one from the other. Okay, we're not worrying about any negative figures here. We just need to deduct them. Now, when you're deducting them, what must categorically happen is that either your x value or your y value must equal 0 once you have deducted one line from the other. In this particular case, when we deduct one line from the other, we can see that we end up with 4x plus 0y equals 2,000. And that's fantastic. However, in your scenario and in your questions, that may not be the case. So let's say that we had a 3 here. Okay, if we took one from the other, we would end up with 4x and 7y and 2,000. That can't happen because we need either the x value or the y value to equal 0. So what you have to do is you have to multiply one or both of your lines to get an equal value to ensure that you can have a 0 at x or a 0 at y. In this case, you can see that if we multiply our bottom line by 2, what we'd then end up with is the following. Department A would remain the same at 8x plus 10y because we wouldn't change it. But department B would then end up at 4x, no it doesn't, 8x plus 6y equals 18,000. Therefore, you have now got a 0x, a 4y and 7,000. Okay? So you can see that we have forced a 0. Sometimes you have to multiply both of your lines. So let's say, for example, that was a 3, that was a 5. Let's say that's a 5 as well. So sometimes, in order to get something that is divisible by both and therefore get a 0, here we could multiply our top line by 3 and our bottom line by 5 to give us 24x plus 15y equals 33,000. 25x plus 15y equals 5 9s are 45. That would give you 1x plus 0y equals 12,000. Again, you've forced a 0 value. Okay, so that's how a simultaneous equation works. You need to ensure that either your x or your y value ends up as 0. As I say, for this example, we've already got 2 of our coordinates the same. Therefore, we end up with 4x, 0y equals 2,000. So, if you think about the calculations that we've repeated now 4 times, we're going to repeat this same calculation again. We now know that if one of them equals 0, we can figure out what the other one is. Therefore, here, because y equals 0, we know that for x must equal 2,000. Therefore, the value of x is 500. 500. So what we now do then to get our y value is we substitute the 500 into our constraint. So if we take the constraint of department A being 8x plus 10y less than or equal to 11,000, what we can now say is we know the value of x, so we can now say 8 multiplied by the value of x plus 10y has got to be 11,000. 8 multiplied by 500 is 4,000, so we've used 4,000 of the hours excuse me, in department A for producing 500x. Therefore, 4,000 plus 10y is 11,000. Therefore, 10y must equal 7,000 because 11 less than 4 is 7. So the value of y must therefore equal 700. So what you've got is the value for x and the value for y. And that is what you've been trying to do all along. Therefore, your coordinates at point C are 500 for x and 700 for y. And if you have a look on your graph, you should see that you are about there. And again, if I just show you my video on the camera, using proper graph paper and using a ruler with straight lines, you can see that point C does in fact sit at 700y and 500x. Okay, so we've just proved that point C is in fact our optimal solution. So your product mix, given the constraints you've got, should be to produce 500x and 700y. But we need to finish off the question. So what we've done is we've identified our optimal product mix is 500x and 700y. Now, how much contribution can we earn? Because we didn't work in profit, did we? We only had contribution values. Well, remember you formulated, you had your objective function all the way back up in O. You had your 4x plus 8y. So if you take that down, we now know that the value of x is 500 and the value of y is 700. Therefore, if you multiply them together and add them across, you will find that you have got an answer of 800, 8 times 700 plus 2,000, 7,600. Okay, this is the maximum contribution that can be earned given the constraint you've got. And if you had any fixed costs, you could take them off and then you see your profit figure. Your optimal product mix is 500 of X and 700 of Y. So we're going to make 500 xylophones, 700 yo-yos. Based on the constraints we've got, it will earn us the most contribution. So we've mathematically identified what our optimal solution is. And we've done that by completing DOF pies. So we define the variables, let x be and let y be. We stated our objective function, which is to show us the maximum sorry about that, guys. This is to show us the maximum that we can earn, okay, in terms of contribution. So we've got 4x and 8y, 4 being our contribution per unit for x, and x being our contribution per unit for y. So this is what we want to do. We want to maximise our contribution or profit. We then formulate the constraints. So we simply take all of the numbers that we've been given and turn them into a sum. So looking at how much of each department or process or resource is being used for each of our products and what the maximum amount is that's available. Remembering to put in there our non-negativity and also any minimum or maximum levels. You then need to state your points to plot. Okay, and we do this by saying when one of our constraints equals 0, then we can make as many as we can to maximise that constraint with the other product, and therefore generating an x coordinate and a y coordinate. We do that for each of our constraints, which then gives us the ability to draw up a graph. We then create an ISO contribution line. And the ISO contribution line is going to show us within our graph and within our feasible region that we've labelled up exactly where the optimal solution is. So we will have labelled our graph showing each intersect within our feasible region, and then our ISO contribution line we push outwards and it will be the last intersect that we pass through. Or if your ISO contribution line were to be on the outside of your feasible region, it would be the first intersect that you come to. You then prove that that's the case by taking the lines that create that intersect at your optimal solution, which are 2 of your constraints, and then produce them through a simultaneous equation. Remembering in your simultaneous equation that either your x value or your y value must equal 0, so you need to multiply your lines accordingly, remembering to multiply the whole line. You can then find the value of either x or y, push that into your constraint to allow you to calculate the other product and therefore giving you your optimal solution and the value of your product mix, which in this case is to make 500 x's, 700 y's, each earning a contribution of 4 for x, 8 for y, giving you a total contribution of $7,600. Oh, just trying to put that in blue. Okay, and that concludes this area of linear programming. You've now seen an answer all the way through. What you need to make sure that you can do is answer that again on your own. Okay, so you need to practice these before you head into the objective test questions, otherwise you won't know where to start. So you need to rework this one. You've then got another apply your knowledge, okay, which I will put on as a separate recording for you. So once you've completed apply your knowledge 2 again, please have a go at apply your knowledge 3. And then you're going to have another recording which focuses on slack and shadow pricing, which finishes off your linear programming knowledge that's required. Okay, and then you've got another question, apply your knowledge 5, which again will have a separate recording to debrief that one for you. Okay, so well done guys, and thank you for listening in.